Two kinds of energy. What are they? What's one of them? Kinetic energy. Good. What's the equation that describes kinetic energy? Every form of kinetic energy, because we don't really differentiate into subcategories here. What's the equation? Tyler. EK equals what? Good. 1/2 mv squared. M being the mass, v being the speed. What are the units for kinetic energy? Joules. Good. Kinetic energy, a vector or a scalar? Good. It's a scalar. The other kind of energy we have is, oops, I gave it away. Potential energy. Now, there's lots of different kinds of potential energy. We're talking specifically about two kinds of potential energy. The kind we dealt with the other day was gravitational potential energy. Anybody remember the equation for gravitational potential energy? Luca? Good. EP is equal to mgh. M being mass, g being what? Gravity. We're going to make that positive, even though usually we make it negative. And the reason we're going to make that positive is because we want our value for EP to be a positive value. Okay? And the reason we want it to be a positive value because EP is a vector or scalar. It's a scalar. Good. There's no direction associated with that. H is height, of course, right? What's the units associated with EP? Joules, same as it is for kinetic energy, right? So it's joules like kinetic energy. It's a scalar like kinetic energy. Now, the other day, seems to me we encountered something that was negative, right? Didn't we have a negative EP? We didn't. No, we had something that was very close to a negative EP, but it wasn't a negative EP. It was a, good, it was a negative delta EP, right? This is going to be positive. Delta EP could be negative. That's the change in potential energy. And if that works out to be negative, hey, that's fair game. That could happen, well, 50% of the time that you're looking for delta E. If it's negative, what did it mean again, Julia? Good. You're not going to get a negative EP for a loss of energy. You're going to get a negative delta EP for a loss of energy. Does that make sense, guys? All right, we'll leave it there right now for a review. We'll spend a couple minutes reviewing the whole elastic potential energy thing in a moment before we do some problems on elastic potential. Let's check over the homework that we had here first that involved gravitational potential energy. 1 to 3 on page 298. Any issues with any of those three questions on 298? Number 3, okay, I figured we'd need to go over number 3. How about 1 or 2? Are they good? 2, okay. Good. All right. Number 2 says a roller coaster trolley begins its journey 5.25 meters above the ground. As the motor tows it to the top of the first hill, it gains that much gravitational potential energy. The mass is 875. We want to know how far from the top of the hill, how far is the top of the hill from the ground? That's a tricky question. Who asked me for that one? That's pretty tricky, isn't it? Kind of the wording of it as much as anything. I don't know about you, but when I see this question, I think like maybe a diagram might be helpful here. Okay, it's not mandatory for a question like this, but if you're having trouble visualizing it, maybe a picture might help us visualize it. So let's do that. We start, here's the ground. We start at this point 5.25 meters above the ground. And it goes up, tows it to the top of the first hill. Okay, we don't know what height this is. We want to know what that height is, but we do know that as it goes from here to here, the change in potential energy is 4.2 times 10 to the 5 joules. Does that make sense? So we're gaining that much potential energy as we go up that height between 5.25 meters and the top of the hill. Good there? You know, while we're at it, we might as well write down the mass of it as well, 875 kilograms, because, look, we got to write down our givens anyways. If we've drawn a diagram, we might as well just put everything in the diagram. All right. Any ideas here? Any ideas? Yep. Good. Good. I'm not going to tell you what I would do in this question. Okay, I think this is a great question, Jeremy, to illustrate One of the things that I've mentioned a number of times, and that is, you may not know exactly where you're going with the question. If you don't, that's okay. That happens to me sometimes. Get something, not some random thing. Don't try saying, oh, E equals mc squared. That's pretty random. Okay. If Jeremy knows he can find the potential energy at the beginning, EP is equal to mgh, then he doesn't need to know. He may know very well where that's going to take him, but he doesn't need to know where that's going to take him. He's just solving for that perhaps because he can. So let's get that. Whether that's what I would do or not, doesn't matter. EP here is equal to mgh, and its value is going to be 875 times 9.81 times the height of 5.25 meters. Jeremy, do you have the answer for that? 064.7? Good, thank you. So we want to have our unrounded number there because that's not a final answer, right? Okay, good, good, that's something. And that's perfectly valid. That's a correct answer for the initial potential energy. Absolutely correct answer. Whether it's helpful or not is another story, but it's absolutely correct for what we've done. Another idea? Is there a way to use that to help us to get what we're looking for? Or maybe somebody's got a completely different idea. Maybe somebody else has got a completely different thought altogether. Great. Oh, okay, interesting, interesting. Okay, we're going to come back and do it again in a second here. Okay, I lied. I said I wasn't going to tell you what I was thinking. Okay, I lied. Jeremiah, I was thinking what you're thinking. Okay, and I was going to do it the way you're going to do it. But Bree, that works as well. To be honest, that just didn't. I hadn't thought of that way. That's all. But it'll work just as well as what Jeremy said. So let's do it Jeremy's way, and then let's come back and do it your way. Okay. We've got EP. Doing it Jeremy's way now with EP. Is there anybody that can think of a way to go from that? Yep, Terry? Good. So we're going to say delta EP is EP final minus EP initial. Okay. And basically we're looking for EP final, right? So we're not going to subtract it. I think you said subtract. Yeah. We're actually going to add it, right? Because, right, does that make sense? It's a negative, so it goes over to the other side by adding. So delta EP, what did it say? It was 4.2 times 10 to the 5. We're going to add to that the initial potential. What do we got here? Yes, we're going to add to that the initial potential, which is 45064.7. And that's going to be, give me what, 8.7064.7. Is that right? We add those two numbers together? No, that's not right. I think it's 4.65. Is that right? 4.65064.7 joules. All right. Now we got the final potential energy, and now we can say final potential energy is equal to mgh final. We've got this. What is that, times 10 to the 5? Uh, 4.650647 times 10 to the 5 equals the mass, which was, what is it? 875 times 9.81 times the final height. Good. I don't know what that works out to be, but that's pretty easy calculation at this point, right? Let's take these over by dividing, and we get it, right? Good? Okay, that works perfectly fine, and Jeremy, that's exactly the way that I was thinking. Okay, but in the end, Bree's way is just as good. No better, no worse. Bree, what was your way?
I just solved for the height.
Okay, so Bree said, basically you're saying, you may not write it down like this, but really what you solved for was not height, but was the change in height.
Yeah, that's
Okay. Now that works because it's not MGH squared, it's MGH, right? If it was a squared, you don't want to stick a delta in there. That's not going to work. Okay, but this works just fine. Solve for delta H there. And what do we end up getting there? Bree, what do we end up getting when we said delta EP over MG? 48.99? 929? Okay. So then what'd you do, Bree?
I added 5.
Good, good. So if this is our change in height, and this was our initial height, then my total height, my final height would be, what, 53, 54? Which should be the same answer as we get over there the other way. You know what? That looks like a bit shorter, actually, a little bit quicker and a little bit shorter than the way that Jeremy and I did it. But I don't care about the length of it. That's irrelevant to me. Okay? I care if it makes sense to us. I'd rather do it a longer way if it makes sense. Now, I wouldn't say that my way does make more sense, but it doesn't really matter, I don't think. Yep.
So I'm going to redo this question instead of adding 5.25, I subtract.
Okay.
What is subtracted?
Okay. No, that's a good question. So you've got to the very end, and you recognize that, look, the change in height is 48 meters. Let's say 48 for simplicity here. And the initial height was 5, not 5.25. Again, just for simplicity. She says she gets to the end and she's gotten this far, and she wants to subtract the 5 meters as opposed to add the 5 meters. Well, there's two ways you can think of that. Two ways that I can answer that question. One is the mathematical way, and one is the logical way. If the mathematical way, we'd say delta H is equal to HF minus HI. Delta H is 48 point whatever. HF is what we're looking for. HI was 5.25. How do you get the 5 over to the other side? By adding, right? So that's the mathematical way. The logical way is to say, well, look, if my height increased by 48, I get my answer of subtracting 5, 43. Well, if my final height, if my change in height was 48, then my final height can't be 43. My final height can't be less than what my change in height was, right? So it has to be added. So let's say you just guessed, kind of like you did. Just check that guess. Does it make sense? It doesn't make sense there, does it? Okay. Everybody okay with that? How many people did it Jeremy's way and my way? Okay, how many people did it Bree's way? Okay, about half and half. All right, finally, let's take a look at number 3 here. A winch pulls a 250 kilogram block up a 20 meter long inclined plane that's tilted at an angle of 35 degrees. What's the change in gravitational potential energy block undergoes? Again, I think it's useful to draw this out. Here's my angle of 35 degrees. I don't know why they'd use an angle of 35 and not 30. Who remembers what sine 35 is out of their head? Not me. 30 is a lot easier to deal with, but whatever. 20 meter long inclined plane. We got a height here of, that's where, oh, I see, yeah. We need this height, don't we? If we want to find the potential energy, we need that height. So let's get that height. Let's say, at least some little trigonometry here, right? Sine 35 degrees is equal to h over 20, opposite over hypotenuse. What's that equal? It's not 10. It's going to be bigger than 10. 11-ish? 11.47? Okay, there's my height. And I could find, now that I have my height, EP is equal to mgh, which is 250 times 9.81 times 11.47. Now, remember, as you solve this, works out to be, I assume, 2.81 times 10 to the 4. As you solve this, remember that you technically haven't found what you're looking for. What have we found there? I found the potential energy at the end of the strip, right? What am I looking for? Not the final potential energy, but rather the change of potential energy, right? If the initial potential energy is 0 and the final is 2.81, then what's the change? 2.81. So although I've technically found the final potential energy, it's the same as the change in potential energy, so we're good there, right? If we were given an initial potential, if we were given an initial potential of, say, 1 times 10 to the 4, what would I do? Would I add it or subtract it to get the change? This is my final potential energy, right?
Yeah.
Okay. Let's say we were given an initial potential energy, not of 0, but of 1 times 10 to the 4. Would I add or subtract to get the change? Yes, yes. And the last question we added, right? But it wasn't to get delta E, it was to get the final. Here we've got the final and the initial, we're going to subtract. Good. Any questions about that? Okay, let's take a couple minutes and go back to spring and elastic potential energy again then for a few minutes. Back when we started energy last week, we said that potential energy was stored energy. The energy that wasn't doing anything right now, but that has the ability to do work later on down the road. Spring or elastic potential energy is the energy that's stored in a spring or an elastic as it's stretched or squished, stretched or compressed. Now, I gave you an equation for that here the other day, but I'll give you that equation again. EP is equal to 1/2 kx squared. Remember what k is? Yep. Yeah, it's the elastic constant or the spring constant, whatever you want to call it. We're going to do an activity here either tomorrow or the next day where your task is going to be to find the elastic constant or the spring constant of a spring. Give you some perspective as to what the numbers really mean. Okay. The elastic constant, the spring constant, we said basically is a measure of the stiffness of the spring. The stiffer the spring, the higher the number. The springs that you're going to use in this activity aren't particularly stiff. You would expect to get a pretty low value for elastic constant or spring constant. Not like 0.2, but like double-digit numbers, not triple or quadruple digit numbers. The stiffer it is, the bigger the number. What's the units for elastic constant, by the way? Yep. Good, newtons per meter. You'll see why in just a couple minutes why it's newtons per meter. Right now, you're just going to kind of trust me on it. X was, we said that was displacement, right? But what do we mean by that displacement? Yep. Yeah, it's not how far it's moved. It's not that elastic flying across the room. It's displacement that way, but rather it's displacement how far it's stretched or compressed. If it starts out 5 centimeters long and it's 7 centimeters long as you pull it, then the displacement would be 2, even if it hasn't physically moved from one place to another. It's how far it's stretched or compressed in meters. Finally, EP is potential energy, of course, measured in joules, and it is a vector or scalar. Scalar. Like all kinds of energy, always, no exceptions. Going to be joules, going to be scalar. All right. If you've got k, you've got x, easy problem to solve. Don't forget to square x, but if you're not careless, it's an easy problem to solve. If you've got k and you've got e and you want to solve for x, a little bit tougher to rearrange. Okay, it's kind of like solving for v in the kinetic energy equation. We've done that before. Okay, tougher but still doable. Sometimes though you want to solve for e and you don't have the value of k. Sometimes we will need to use another equation in order to solve for k first. And this is going to be the first time you've seen this one. It's called Hooke's law. Hooke's law provides for us a relationship between the force applied on something and the displacement of that something. Hooke's law, context of a spring, Hooke's law says that basically the bigger the value of x, the more you stretch something, the more you stretch the elastic, the bigger F has to be. And I think that's logical, actually, right? You try pulling a spring or an elastic back. You guys know that the more you pull it, the harder it becomes to stretch, right? The more you pull it, the more force is required. This may not seem like a big deal, but this is actually something different. It's pretty different than what we've done before. We've had a force of 10 newtons over here, another force of 20 newtons over here, sometimes acting on the same object. But the force was the same the whole time. The force that you pushed on an object was either 10 or 20. It didn't change from 10 to 20 in the same question. It wasn't changing. Whereas a Hooke's law, the more you pull the elastic back, the more force is required. So depending upon what the displacement is, that's going to determine what the force is. When a car is driving down the road, its displacement does not determine its force. When we're pulling an elastic, the displacement does determine the force. It's a form of what we call simple harmonic motion that we'll take a look at in our last unit in a little bit more detail. What's K stand for? The spring constant, or the elastic constant, whatever you want to call it, newtons per meter. X is the displacement again. Can't spell it, but shouldn't be that hard to spell. It's going to be measured in meters. And F is, of course, going to be the force. What you're often going to see here in these questions is a rearranged form of this equation. K is equal to F over X. You'll be given the value of F, given the value of X. You'll have to plug them into here to solve for K, and then take that value for K and plug it into here to solve for EP. It's kind of a two-stepper. We don't always see that, but we sometimes do. All right? Now remember here, F is not an average force. F is the force at a moment in time. When the displacement is 2 centimeters, here's what the force is. When the displacement is 4 centimeters, here's what the force is. The two forces are different. Okay, F is not the average. F is the force at one moment in time when the displacement is whatever it is. Be prepared for this, be prepared for this, and be prepared for a combination of those two. All right, let's do an example here. 6.4, page 301. Spring is stretched to a position 35 centimeters from its equilibrium position. Notice I circled that centimeters. Why did I do that? Why did I circle that centimeters? Yeah, it's got to be in meters. And you know what? In my experience, I just told you guys a little while ago that when we go to our field trip on May the 29th, that'll be my 35th amusement park field trip. This is my 40th semester. My 40th semester. Thursday was my 40th parent-teacher interviews. This is my 40th semester. By now, you would think that maybe I've picked up on some common mistakes that people make. You would think. One of the mistakes that people make commonly is forgetting to convert units. So what I've found works is if you draw attention to it, right? Now, it's hard for you guys right now when you're sitting at your desks because it's up on the board, right? It's hard for you to circle. But I do that when it's up on the board because I want you to remember when you get a quiz or a test, I want you to remember, circle it. Draw attention to it somehow because it makes you less likely to forget to convert. Doesn't mean for sure that you're not going to forget, but there's less chance of it. So we got 35 centimeters from its equilibrium position. At that point, the force exerted is 10.5 newtons. What's the elastic potential energy? And if the spring is allowed to reduce to 20 centimeters, what's the change in potential energy? That's a good question. That's a good question. It's not as trivial as you would think we'd start off with. All right, let's look at A first. Let's forget about reducing it to 20 centimeters, okay? We'll deal with that later on. We've got a force here of 10.5 newtons. That's actually, by rights, we should put an absolute value around that because we don't actually have a direction. We're just told, here's the magnitude of the force. Now, if you don't put that absolute value around it, meaning magnitude only, we're not going to lose any sleep over that. Okay, I wouldn't take off a mark if you didn't do that. Okay, if you just said F is 10.5 newtons, that's okay, but this is a little bit better. My displacement is 0.35 meters, or 35 centimeters. And I got to find EP. Remember, I haven't done anything with B yet. Focusing on A right now. We know that EP for elastic potential is 1/2 K x squared. It's 1/2 of, I don't know what K is. I know what X is. I don't know what K is. Ideas? Ideas? Joseph? Yeah, let's use Hooke's law. K is equal to F over X, right? 10.5 newtons over 0.35 meters. That works out well, I think. 10.5 divided by 3.35, I think, is 30, isn't it? And the units for that would be, hey, remember what we said? They're newtons per meter? Remember I told you, trust me on that for now. In a few minutes, you'll see why it's newtons per meter. Can you see why K is newtons per meter now? Because it's F over X, right? Newtons over meters. Okay, let's plug that in now. $1.84. Let's go the unrouted number just in case we end up needing that. 1.8375 joules, which will round to 1.84 joules. Okay, good. A's done. Now let's have a look at B. If the stretch in the spring is allowed to reduce to 20 centimeters, what's the change in elastic potential energy? What do you think you're going to do here? What do you think you're going to do, Jordan? What do you think you're going to do here? Okay, so we have the initial here, right? It's 1.84. So you're saying get another EP? Okay, let's do that. Let's for B, we'll do this one in red. For B, let's say EP is equal to 1/2 times, oh, wait a second here. What's K? Do we have to do that again? Is K now, K would now be what? 10.5 newtons divided by 0.2 meters, is that right? Is that right? No, K is K. When the displacement was 35 centimeters, the force was 10.5. When the displacement's 20 centimeters, the force is no longer 10.5 newtons. I don't know what the force is now. It doesn't really matter, because in the end, I've got the value of K. I don't need to find it again. It's just 30 newtons per meter. Think of that. Think of it, guys. I told you the spring constant is a measure of how stiff the spring is. That's a property of the spring. How far you stretch it affects what the force is, but how far you stretch it doesn't affect how stiff the spring is. So in other words, the spring constant is the same for the spring no matter what. Unless, can anybody tell me when the spring constant for the spring would actually change? I'll give you a little hint. We won't be solving any problems in which it will. But can you tell me when it might? Yeah, it could. Yeah. I was thinking of something else, but that could be a little bit. It'd be a pretty minor effect, but. You ever done this to a spring? Pull it back and it's like, oh, I just wrecked it because you pulled it back too far and you bent it. Well, then all bets are off then, right? You've completely changed the nature of the spring at that point. Make sense? Kind of analogous to pulling the elastic back and snapping the elastic, right? All bets are off then. So spring constant is going to be the same here. Now our displacement is 0.2 meters. Let's get EP there. 0.60 joules. All right. Jordan, Mr. I think I know everything on that question. What would I do now? Oh, so he does actually know everything on that question. Yeah, you're right, Jordan. Good. You'd subtract the two. 1.84 joules minus 0.6. Actually, no. I'm wrong here, actually. What have I done wrong? Jordan, you know exactly what you're doing there. What have I done wrong there? I flipped them. It should be final minus initial. What did I do? Initial minus final, right? So it should be 0.6 minus 1.84, which gives me negative 1.24 joules. What's the negative mean? A loss of energy. It's not stretched as far. Of course it's a loss of energy, right? Good. Jordan, good. Yep. Hey, I think A is a little bit tricky because you had to find K in there. I think B is trickier. Doesn't look so bad. Hey, find a potential energy, subtract it. That's easy enough, right? But how many people do you think, if I had given you this yourselves, how many people do you think would have solved for a new K? K is equal to 10.5 over 20 centimeters. You know what, Jordan? Hey, if I was in grade 11, I probably would have. I probably would have made that mistake if I didn't know any better. I've learned this enough time and taught this enough time that I know better. Make sense though, guys? Once you find the spring constant of the spring, it isn't going to change. So don't come up with a new number for displacement just because there's a new displacement. All right, let's see what you can do with these 5 practice questions.